Hello, this is the mind map for Year 9 Earth and Space Science. If you want to take a snapshot now, you can. Otherwise, we're going to zoom in. All right, first of all, we're going to start with the layers of the atmosphere. The first layer of the atmosphere is called the troposphere. It extends 15 kilometers into the sky. The temperature decreases with altitude, and this is where weather occurs. The next layer is the stratosphere. It extends up to 50 kilometers into the sky. It contains the ozone layer, which absorbs UV radiation from the sun. The temperature increases with altitude as ozone absorbs the heat. It contains satellites. The next one is the mesosphere. It extends 85 kilometers above the Earth. The temperature decreases with altitude, and this is where meteors burn up. The next layer is called the thermosphere, which is super important. It extends up to 600 kilometers in altitude. The temperature increases with altitude up to 2,500 degrees Celsius as it's nearer to the sun. It contains the magnetosphere, which is the magnetic field of the Earth, which reflects and deflects the solar wind from the sun. It also contains the ionosphere, in which auroras occur. The last layer is called the exosphere, and it extends into space. It's very, very cold at minus 273 degrees Celsius, which is absolute zero. All right, then we actually get on to the auroras. We can see here in the diagram, the sun is expelling the solar wind, which is charged electrons and protons, and as it hits the magnetic field of the Earth, it gets deflected down to the poles. All right, so up here on our mind map, we've got energy is ejected from the sun as a solar wind and as solar flares. It travels at the speed of light to reach the Earth within 8 minutes and hits the Earth's magnetosphere, then gets deflected to the poles, where the magnetic field is the weakest. The solar wind hits the ionosphere, which makes the electrons in nitrogen and oxygen jump up to a higher level, and as they fall again, they emit light. Nitrogen emits red and purple, oxygen emits green. Next up, we've got the structure of the Earth. We'll start in at the center. We've got the inner core, which is 1,300 kilometers thick. It's made of solid iron and nickel, and it's solid due to the intense pressure. Next, we've got the outer core, which is about 2.2 thousand kilometers thick at 5,000 degrees Celsius. It's made of molten iron and nickel. Next, we've got the mantle. It has a thickness of 2,900 kilometers. It has a variable temperature ranging from 1,000 to 3,700 degrees Celsius. The inner part is solid, but the outer part is liquid, and it's in this liquid part where we have convection currents. Then at the top of the mantle, we've got the asthenosphere, which rubs against and drags the lithosphere, allowing for continental drift to take place. Then we have the most outer layer, the crust, has a variable thickness ranging from about 8 kilometers to 40 kilometers. We've got oceanic plates made of basalt, which are quite dense, and we've got continental plates made of granite, which are less dense than the oceanic plates. All right, then we go down to the major plates of the Earth. I've got a little diagram here of the plates. We've got the African plate, the Antarctic plate, the Eurasian plate, the Indo-Australian plate, the North American plate, the Pacific plate, and the South American plate. Right, then we go up to the top here, and we can see that we've got about convection currents. We see here that the core supplies the heat, and it heats up the magma, and as the particles gain energy, they move faster. This decreases the density and the particles rise. As the magma reaches the top, it is pushed to the side, and as the magma cools, the density rises and the magma sinks. It's a continuous cycle, and it's this convection current that drives continental drift. Now, in continental drift, 335 million years ago, Pangaea was formed, and 200 million years ago, Pangaea split into Laurasia and Gondwana. 150 million years ago, the mid-oceanic ridge formed in the Atlantic Ocean, and 150 to 65 million years ago, South America and Africa separated, making the Pacific Ocean. Also, 150 to 65 million years ago, India moved towards Europe, and 150 to 65 million years ago, Australia and Antarctica started to separate. Then 50 million years ago, India smashed into Eurasia, forming the Himalayas with fold mountains, and Australia continued to drift north towards the equator, making it hotter and drier. Evidence of continental drift, well, we've got magnetic striping from the mid-oceanic ridges. Every 10 million years, on average, the magnetic poles of the Earth flip, and the iron within the sea floor also flips in its alignment, and we can see this striping as we move away from the mid-oceanic ridge. Also, all continents fit together like a jigsaw, indicating that they were all once joined. Also, we've got fossil tracks, again, that were all connected together because the world was only one large continent called Pangaea, so these fossil tracks all link up, as do glacial traits of different continents lining up together, indicating they were all once joined together, and this is occurring around Antarctica. Then we've got different plate boundaries. There are 3 different types of plate boundaries. There is diverging, converging, and transform. Diverging makes new crust, and when it does so, earthquakes are possible. Diverging, there are 2 types. There's the mid-oceanic ridge, which allows for seafloor spreading, and we've also got rift valleys, which makes new land. With converging, this is where 2 plates are colliding. If we've got an oceanic plate and a continental plate, it forms a subduction zone because basalt is denser than granite and therefore subducts underneath the continental plate. A trench forms in front of the land and volcanoes are formed inland. When a continental plate and a continental plate, or an oceanic plate and an oceanic plate meet, because they're of equal density, fold mountains are formed as the crust pushes upwards. In a transform plate boundary, 2 opposing plates generate friction. The sudden release of friction causes an earthquake. Then we move on to natural disasters. The first type of natural disaster is to do with volcanoes. There are 3 types. There is the shield, the cinder cone, and the composite, depending upon their structure. Here we have the cinder cone, the shield, and the composite. A magma chamber builds up pressure under the volcano, and the release of lava through the central chimney and the vents allows for the escape of the lava. The eruptions are normally preceded by an earthquake. Earthquakes, again, is the build-up of pressure under the Earth. The epicenter is above the focus, and the focus is the site of the disruption. Well, we've got 2 waves that come out. First of all, we've got the P wave, which is longitudinal, and we've got the S wave, which is transverse. And here we can see that the movement of the P wave shakes the Earth from side to side, and the S wave makes the Earth move up and down. Here is the diagram of the epicenter above the focus. And then the earthquake is recorded by a seismogram using the Richter scale. Next we have tsunamis, which is caused by the displacement of water. The waves radiate outwards in all directions, and the size of the wave equals the volume displaced. But when the water is out at sea, and the sea is deep, we've got a long wave, and when the wave comes into the shore, because the shore is shallow, the wave gets taller. Next we have geothermal energy, in which we pump cold water over hot rocks. This generates steam, then the steam comes back up to spin a turbine, which spins a generator to generate electricity. Here is the diagram of geothermal energy. Thank you for listening.